of Ana Sánchez PhD thesis. This thesis has been supervised by Doctors Belén Riveiro and Pedro Arias, and the examination committee is formed by Dr. Lucia Diaz and Dr. Roderick Lindenberg, and myself, Jose Adam. Before proceeding with the presentation of the thesis, let me explain how this event will be organized. All microphones and cameras must be disconnected while Ana is presenting her thesis. And after the presentation, a debate will take place between Ana and the committee. Then, doctors in the meeting room will be invited to participate with comments or questions. And finally, the committee will leave this room for the deliberation. Ana, I understand that you know all the rules applicable to this presentation. Am I right?
Yeah.
So, Lucia, as secretary of the committee, would you like to add something before starting with the presentation?
No, I think it's not necessary.
Okay, that's right. So, Ana, you can proceed with your presentation. Thank you very much.
Okay, thank you. I will now change my camera and I will start sharing my screen, so it will take me a minute or two. Now here you have my camera and I will start now sharing the screen. Let me know when you can see the presentation, please. It's loading a little bit so I can see.
It's perfect.
Okay, right. Thank you. Well, with the permission of the tribunal, I will start now with the presentation of my doctoral dissertation entitled Automated Structural Inspection of Facilities Associated to Terrestrial Infrastructures Networks from Geometric and Radiometric Data Acquired by Laser Scanning Systems. I will start first making a summary of the parts. It is divided in 4 main parts, starting with an introduction and its main objectives, following by the methodological development, in which the papers, the publications of this thesis are going to be presented, and ending with the conclusions. So as a start, let me explain you a little bit of my career. This thesis is under the Inter-University Doctoral Program in Geotechnologies applied to construction, energy and industry. And I work for the area of materials engineering, applied mechanics and construction. And through this area, I give practical lessons in the School of Industrial Engineering. Although I started my PhD in September of 2016, I've been granted with a predoctoral scholarship from the University of Vigo in February of 2019. Through these years, I've developed 3 different research stays. One of them in the University of Minho in Portugal, another one in TNO in the Netherlands, and another one in the Technical University of Munich in Germany. And moreover, through these years, I've also been working in different projects, being the most important ones in this case. The first of them is Tunnel Curiosity, which allowed me to start with my thesis and also allowed me to get an insight of what is to work for a private company. And moreover, as a continuation, I'm working in Safeway currently. It is an European project in which the University of Vigo is the coordinator. And now let's move on to the motivation of my thesis, starting with the first part of this presentation. As you may know, the evolution of society is extremely dependent on the transportation network, being so important to guarantee its good functioning and service. Moreover, since most of the daily activities depend on the transportation network, it is important to have safe, efficient, and sustainable infrastructures. In Europe, specifically for land transportation, we have more than 217,000 kilometers of railway lines and more than 77,000 kilometers of motorways, forming the Trans-European Transport Network, the so-called TEN-T. And for this distribution of routes, it is logical to think that the historical heritage is very important. It's really important in Europe. The Roman Empire expanded its power by creating a path network across Europe that connected the entire empire with Rome. These routes are still taken as basis for current transportation networks. One of the main assets created by the Romans are masonry arch bridges. These bridges allowed to create short routes and across rivers, among other obstacles. And since a lot of them are still standing, it is important to make good inspection and maintenance of these structures to guarantee their good functioning for service. Another significant milestone for land transportation was the appearance of the railway infrastructure after the Industrial Revolution. The appearance of the railway network allowed to reduce costs for infrastructure and also time. Another, as with bridges, tunnels are an asset that is really important in this network because tunnels were created as a necessity to save a natural barrier as it could be a mountain, although nowadays we don't use it entirely with that end. There are special characteristics. The special characteristics of these assets make them important to be monitored in specific ways because of their location and geometrical characteristics, because a failure inside them could be fatal and also could provoke long cuts in the service. Taking into account the characteristics of these assets, it is really important to monitor their operating conditions during their entire life cycle. For that, the ideal would be to have resilient infrastructures. These resilient infrastructures could be able to anticipate, to respond, and to minimize or even mitigate the effects of extreme events. Now, all this is summarized in this thesis in three main steps. In order to achieve this, an investment in the preservation of the transportation network is needed, and the application of predictive maintenance could be also a good point in order to better inspect these infrastructures. Moreover, the second step would be the use of the development of new techniques and the use of new surveying technologies in order to monitor the as-is state of critical assets. And finally, the digitalization of information using always international standards. All this will allow to inspect and monitor assets in a safer way and without the subjective opinion of a technician. And all this was summarized in the thesis as one main objective, which is the development of new strategies for the structural inspection of aging constructions and monitoring of the railway line. This main objective was segmented in 4 different ones, being the development of general algorithms applicable to any 3-dimensional point cloud, the creation of methodologies for the optimized analysis of registered point clouds of different structural systems or elements. The third step would be the development of inspection algorithms for describing the as-is state of an asset. And finally, the use of point clouds for generating digital models of infrastructure. And with this, after this short introduction and the presentation of the main objective, the next step, the next chapter of the presentation is the methodological development. It is divided in 4 different sections, being the first of them a context, and the other 3 of them are a summary of the 6 publications presented in this thesis. This is how they are going to be structured, and these are this is their structure also. I will start with a short introduction to point cloud processing. The second chapter, the second section, is formed by 3 different publications. The third section is formed by 2 publications, and the 4th section is formed by 1 publication. So let's start making a short introduction to point cloud processing. As you may know, my thesis is based on the use of 3-dimensional point clouds, which are radiometric and geometric data acquired by laser scanning systems. The systems that we have used under this thesis are terrestrial laser scanning systems and mobile laser scanning systems, although aerial laser scanners also exist. Moreover, these terrestrial laser scanners are based in the LiDAR technology, and the result of applying, of surveying these assets or the required infrastructures are a matrix of data, which are the so-called point clouds. This matrix of unorganized data are formed by the geometrical characteristics of the assets as coordinates, and another characteristics as might be the intensity of the reflected laser pulse or the timestamp. In this thesis, I've only been working with the coordinates of each point. And moreover, when working with mobile laser scanning systems, I've also been working with the trajectory. Okay, so what do we do now with that data? We get, this is the process followed by anyone working with point clouds. The first step is to get the input, which is a point cloud and a trajectory for the case of mobile laser scanning systems. These data are used as an input for the program, in which different algorithms are applied for segmentation, classification of data, or even a semantic characterization of them. And finally, an output is obtained by obtaining labeled data, classified data, semantic information, or whatever we are trying to get out of the point cloud. This is a process that everyone working with point clouds follows. So the next, as a general objective that I presented, was the explanation of some general algorithms applicable to any 3-dimensional point cloud. Although I didn't invent the wheel here, it is important for me to explain you some of these processes, since they are very relevant for the consecution of this thesis and for in order to get results using the developed algorithms. So let's start explaining the first of them, which is the voxelization. The voxelization is the creation of a cubic grid in the 3-dimensional space of a point cloud, and then the size of the point cloud is reduced in order to obtain only one point inside each cube or each voxel. That point is obtained as the center of gravity of every point inside the voxel. Another algorithm would be the application of dimensional analysis. This procedure is used, it is a statistical procedure, and it is used to classify points in order to it's used to classify points based on their probability of being part of a linear, a planar, or three-dimensional element. And how do we get this information? By using the eigenvalues and eigenvectors obtained by another statistical procedure, which is the principal component analysis. This analysis allows us to obtain these values and these vectors, and this, in my case, I've applied the principal component analysis based on the obtainance of the covariance matrix of the point cloud. Another simple method developed is the rotation of a point cloud. As you can see here in the slide, we can see a point cloud looking at it from the top part. Each point cloud has a main direction, a principal direction. This direction can be computed by applying, again, principal component analysis, or by using the main direction of the trajectory of the laser scanning system. For the case of, in my case, when working with mobile laser scanning point clouds, I've been using the main direction of the trajectory of that section of point cloud to perform the rotation. If not, if working with terrestrial laser scanning point clouds, I've been using the principal direction of that point cloud. And the result is very simple. The point cloud ends up aligned with an axis, the y-axis or the x-axis, depending on the angle, the rotated angle. Another important method used during the consecution of this thesis is the random sample consensus, better known as RANSAC. This is a mathematical procedure. It is an iterative procedure which is based on fitting a model to some data set. How do we do this? It is formed by 4 different steps. The first of them is to randomly select a subset of data, then fitting a model to that subset of data, and third would be determining how many outputs are outside that fitted model. And then this procedure, these 3 steps, are iteratively repeated, a number of iterations based on a predefined number that is given to by the user. Here in this slide, you can see a line that ended up as the best fit, which has the most, the biggest number of inliers. And in here, you can see that also this procedure also allows to fit polynomial models. And finally, I would like to present you the Silency Analysis. This analysis, it's based on comparing some vectors of the point cloud in order to segment the ground, the horizontal points of the point cloud. How is this done? Well, the normal vector of each point, the distance between the normal vector of each point and the vertical vector 0, 0, 1 is measured, and that distance is projected into the hyperbolic tangent function space. And with that, we obtained a saliency map that allows us to classify points regarding to its saliency. With that, we obtained the ground points classified. And with that, we end the first subsection of the 3rd chapter of this presentation. And we can continue to the 2nd chapter, which is the first one that contains information about the publications done in this thesis. This chapter is about the detection of faults in masonry structures. The objectives of this chapter, as you can see in the slide, the summary is that we want to obtain algorithms that allows us to classify elements, to classify point clouds into the elements of masonry arch bridges, and also to inspect these bridges, the piers of these bridges, and the walls, masonry walls. So this is performed by 3 different publications, being the first of them, this one, the detection of structural faults in piers of masonry arch bridges through automated processing of laser scanning data. This publication, it's a journal article. It has been published in the journal Structural Control and Health Monitoring in the year 2017. Sorry. How is the workflow of this publication? It starts with a bridge point cloud, and then classification algorithms are applied. First, a rough classification of points is done based on their elevation angle, and then applying another classification procedures, different elements are obtained. And once the piers are isolated, each of their faces can also be segmented in order to be able to detect the possible damages affecting these piers. So let's start to explain a little bit more specifically this methodology. It starts with a point cloud like the one in the slides, which is a terrestrial laser scanning point cloud. What we want to do first, as the first step, is a classification based on the elevation angles of each point. How do we obtain these elevation angles? Well, first we applied a voxelization of the point cloud in order to reduce its size. Then we applied the principal component analysis in order to get the main components of a point cloud, the eigenvalues and the eigenvectors. And these principal components, it is important to know that the third component is the normal vector of each point that has been calculated. I know that a point cannot have a normal, but this normal is calculated taking into account the neighbors of each point being studied. So once we have the normal vector of each point, the elevation angles and the azimuth angles, the orientation of that vector can be calculated. Once we have the elevation angles, 2 main group of points are obtained, as you can see here in this image. And now the next step is to work only with the points, the elevation points. Sorry, I heard a noise. So working with the point cloud of vertical elements, we can perform the azimuth and azimuth angle classification. First, the group studying those values of azimuth angle, the group that has the biggest number of points is the spandrel walls. The next step is to classify piers and cutwaters, and these are separated, creating a bounding box around each pier. I'm hearing a noise. I don't know if that's for me or not. Sorry for that. I guess it's not. Okay. So the bounding box, contained piers and left out cutwaters, and that's how we classify these points. And then, working with the point cloud of non-vertical elements, we can perform a dimensional analysis and a classification based on the set coordinate of each point to obtain the results of the classified bridge, as you can see here in this slide. So now let's move on to the classification of the segmentation of piers. Once we have the piers isolated, the next step is to distinguish each of their faces. How do we do this? Well, we have the azimuth angles of each point in the piers, and moreover, we have the bridge orientation. The bridge orientation is calculated based on the azimuth and elevation angles of the spandrel walls, because these elements are the most representative of the orientation of the bridge. Once we have that, we perform a coplanarity analysis in order to distinguish the longitudinal and the transversal faces of these piers, obtaining as a result this classification, as you can see here in this slide. So now that the piers are classified, the next step is to perform the damage detection. We have calculated from the previous step the angles of the bridge and the angles of each of the faces of a pier, and it is logical to think how should be the angles of each face if they are not suffering from any damage. Taking that into consideration, an investigation was made in order to make a review on which are the most significant damages that can happen in this type of bridges, in the piers of this type of bridges. That gave us, as a result, a damage matrix, as you can see here. Here you have a closer look of that damage matrix. And the summary of this matrix is that each possible damage has a different configuration in the angles of each face of the piers. Based on that, the possible damages were obtained. Obtaining, let me show you first the results of the classification. Here you have a comparison of the results obtained for the classification of the whole bridge and the classification of each pier's face. And here you have an example of the damage detection of a bridge. It is the Roman bridge of Segura, and this bridge was selected because it has been previously studied in other campaigns by experts, and I can say that the results obtained are aligned with those obtained by the experts in previous campaigns, as you can see in the publication of this paper. So now let's move on to the next article. This is a conference article presented in the 11th International Conference on structural analysis of historical constructions. It was in 2018 in Peru. This publication is based on the detection of out-of-plane deformations in straight masonry walls. This is the stretch of the wall that has been surveyed. It has a total length of 230 meters, and the external face has been entirely scanned, but only a stretch of the internal face was scanned. This survey was performed using a terrestrial laser scanning system, and in this image you can see that we have a difference in height in the internal face of the wall. This is important when obtaining the results. Well, how do we perform? How do we do this methodology? First, we have to do a classification of points in order to get rid of points belonging to the ground that we are not interested in. That is simple. We apply the voxelization of the point cloud, and then we apply a saliency analysis. As I explained in the beginning, this saliency analysis creates saliency map, and the ground points can be easily classified. After this classification, the damage detection is performed. We are going to be measuring out-of-plane deformations. And how do we do this? I fitted a plane between the two faces of the wall, and then I measured the distance from each point in the walls to the fitted plane. The results are reflected in two images. These images here, which I obtained voxelizing the point cloud and then transforming those voxels into 2D, two-dimensional pixels to form the images, and the values of each pixel are the mean of the distances values inside each of those voxels. Here you can see a graphical comparison of the results obtained. These have been measured at different heights of the wall, and you can see that in the previous slide. Here you can see that the left part of the external face of the wall is clearly damaged. So taking into account and focusing on that part of the wall, we get to these results. This graphic represents the distances obtained at the height of the red line that you can see in your screen. And as you can see, both faces of the wall, the external and the internal face of the wall, are opening following almost the same curve, although the external face suddenly suffers a peak of distances. This happens along the whole height of the wall. These are the results obtained for this conference paper. And now let me present you the last publication of this section of the presentation, which is a book chapter published in the book Long-Term Performance and Durability of Masonry Structures. This publication is a summary of the work developed until now, until this moment. It summarizes the state of the art of laser scanning, of applying laser scanning to masonry structures, and which applications can be done using this laser scanned data. These applications are, in order to detect superficial pathologies, we can use the intensity values in order to detect, as you can see here, the humidity or fluorescence. And then we can also make an analysis of the structural damage of some masonry constructions as the ones that I presented before. And with this, we get to the conclusion of this chapter, which is that we have been able to develop algorithms for classifying point clouds of masonry arch breaches, and also we have created algorithms in order to analyze the state of piers of masonry arch breaches and straight walls. This puts an end to the second chapter of the second section of this chapter, and we can start talking about the third section of this chapter, which is the classification of railway tunnels. The objectives of this section are the development of classification functions in order to make an inventory of tunnel elements from point cloud data, and the analysis, the inspection of the power line of railway tunnels. This has been performed by publishing 2 different journal articles. The first of them is the automated detection and the composition of railway tunnels from mobile laser scanning datasets. This publication is a journal article that has been published in the journal Automation in Construction in the year 2018. The workflow, it's very simple. We start with the tunnel point cloud and the trajectory, because in this case we are working with mobile laser scanning point clouds. And then a preprocessing is needed in order to start with the classification of points. Then this classification is performed by first doing a thresholding and a saliency analysis to obtain 2 main group of points, and finally performing different classification algorithms, the results are obtained. So let's start talking about the preprocessing of these point clouds. Some filtering has been done in order to delete some noise, and a downsampling was made in order to give homogeneity to the point cloud. And then a trimming was made because these point clouds were very long. They have kilometers. We have kilometers of tunnel point clouds, so they were trimmed in order to obtain 20-meter long sections, and then these sections were rotated, applying the algorithms explained at the beginning, in order to ease some classification procedures. And then we can move to the classification methodology. This methodology starts with a section of 20 meter long section of a point cloud, as the one that you can see here in the slide. And apart from having this point cloud, we also have the trajectory data, the position of the scanner inside the tunnel. And the first thing that we do is perform a thresholding in order to classify, to obtain two different groups of points. We working with the part of the point cloud that is under that trajectory level, we can perform a Silency analysis to those points in order to obtain, as you can see in the slide, the classified points belonging to the ground. Now, working with those ground points, here you can see them from the top. Working with those ground points, a curvature analysis is made. This curvature is calculated using the eigenvalues of the covariance matrix of the point cloud, calculated applying the principal component analysis. These values have been represented in a graphic, as the one that you can see here. And in this graphic, we can easily detect the peaks of curvature in which part of the point cloud we have some changes in the values of curvature. Taking this into account and knowing the track gauge, the normative track gauge in Spain, a threshold of 170 millimeters is applied in order to obtain as many possible rails as peaks were in the previous graphic. How do we detect now which of these possible rails are the real rails? I've applied a support vector machine algorithm. This is a supervised machine learning algorithm. In this case, I've applied a linear kernel, and I've been using I've tried two different features vector, one from the state of the art, the first of them, and the second created by the authors, which was the one proven to give better results in the classification. And after the training, we obtained the trained model, and using that model, we are able to classify correctly the real rails of the point cloud. Now, the next step is to classify the non-ground points. This is very easy. What I did was to perform first a dimensional analysis. This dimensional analysis, as I explained in the beginning, classifies points in three different groups of data, depending if there are part of a linear, planar, or three-dimensional element. Now, working with the point clouds classified as a surface, we obtained the classified lining, the lining points. And next step would be to classify points from the power line and the cantilever points. How do we do this? Applying Ransack, as I explained in the introduction, to fit aligned to the data. This is the result obtained. We obtained the power line classified, and then a connected component analysis is done in order to distinguish different groups of points and left out outliers, to clean outliers out of the power line point cloud. Once the power line was classified, the same procedure was applied to detect cantilever arms in the clouds in the sections of the point cloud that had them. And these are the results of the classification. You can see here a different color depending on the element that the points belong to. We have in this slide a summary of the performance metrics obtained. And this, it is important to highlight that this methodology has been tested in 3 different tunnels, obtaining different results, but very similar for each of them. You can see, you can better analyze them in the paper. And here I wanted to show you the difference in the classification of rails. This is a point-by-point comparison. You can see in blue the automated classified points, and in red the ground truth that was obtained by hand. This difference is clearly noticeable, but I wanted to say that it is also reflected in the performance metrics, but this difference can be reduced by applying a smaller thresholding when detecting the track gauge. And now let me go directly to the next publication. It is also a journal paper. This was in charge of inspecting the railway tunnel point cloud. Sorry, the railway tunnel power line. It was published in the journal Remote Sensing in the year 2019. And I wanted to directly come to this publication since it is based in the previous one of working with the results obtained from the previous methodology. We used the power line point cloud and the cantilever point clouds to perform a further classification of points to detect the contact wire and the suspension wire in the power line point cloud, and finally to perform some inspection measures in these cables. Now let's explain better the methodology. In this image, you can see a graphic representation of the wires that we want to detect, the contact wire and the catenary or suspension wire. And here you have how a point cloud would look like once it is classified. We have the power line in orange and the cantilever arms in blue. Now, what we want to detect first is the contact wire, the one at the bottom. We work with the power line point cloud and we applied RANSAC to detect, to fit a line to this point cloud. And with that, we directly obtain the classification of the contact wire. Next step would be to classify points belonging to the suspension wire. How do we do this? We have to take into account that the suspension wire points are the highest point in the power line point cloud, but it can happen that we can have a cantilever arm in this point cloud. So in that case, we want to perform a classification, a segmentation of the point cloud in two parts, one before and one after the cantilever arm. After that, we perform a trimming of 5 centimeter sections along the point clouds, and taking into account that the suspension wire points are the highest points in the cloud, we used a MATLAB algorithm, the range search, in order to look for the nearest neighbors of the highest points in the cloud. The radius applied is equal to the suspension wire diameter for our case. Applying this, we obtain the suspension wire, the classified suspension wire. So now let's move on to the part when we inspect this power line. The measures that we want to do is the gauge measure and the deflection of the catenary. This is a graphic explanation of what do we want to measure. And here you have a representation of the same, but in the form of a point cloud. We have the rails at the bottom and the power line at the top part of the point cloud. So let's start with the classification, with the measurement of the clearance gauge. For that, we want to detect first the rail's top surface. In order to do that, we apply the voxelization to the rail's point cloud, and then we look for the voxels with the highest set coordinate. Then, once this surface is detected, we fit a plane to those points, and finally, the Euclidean distances from the plane to the contact wire are measured. This is a graphic representation of how I did this. And let me present you now how did I measure the deflection of the suspension wire. The first step, since I have 20-meter long point clouds, I had to find in which of those sections I had a cantilever, and moreover the point clouds inside them, taking into account that the biggest span in Spain is equal to 50 meters. Once I did this, next step was to fit a line to the highest points in the span. Once after this, the deflection measure was directly computed by measuring the Euclidean distance between each point of the suspension wire to the fitted line. And with that, we obtained the results of the deflection measure. Here you can see a summary of the classification results obtained in a point-by-point comparison. Also, this methodology was proven in 3 different tunnels. And here you have a graphic representation of the gauge measurement results. And I can say that every measurement performed was inside the normative limits imposed by the norm in Spain. And the same can be said for the deflection measures, since all of them are under the maximum permissible deflection value. Okay, with this, I put an end to this section of the 3rd chapter of the presentation. And as a conclusion, I can say that I have obtained methodologies. I've created methodologies for the obtention of classified point clouds, tunnel point clouds, and moreover to perform the inspection of the catenary of the contact wire, of the power line of the tunnels. And after the 3rd chapter of this section, let's move on to the digitalization of information with the 4th section. The objective of this section is to use point clouds for generating digital models of infrastructure. This chapter is formed by only one publication, this one here. It was presented in the 27th International Workshop on Intelligent Computer in Engineering this year in 2020. The workflow, it's very simple. We start with bridge point cloud, Masonry arch bridge point cloud. We perform some classification algorithms to the element of the cloud, and then we convert those classified point clouds into mesh and then into IFC models. This is the methodology followed by the classification of points. I will not spend too much time in this, since it is based on the first that I explained, on the one that I explained at the beginning of this presentation, although it has been improved to obtain better results. This can be further studied in the paper. But basically, it's based on the analysis of the orientation of each angle of the elements of the bridge. Once these elements were classified, the segmented point clouds were, the next step is to convert them into a mesh. How do we did this? Well, the first step was to make a preprocessing of the point clouds in order to clear some noise that could be inside the point cloud, and then depending on the purpose of the mesh, a different level of detail can be obtained. For the case of level of detail 500, what we did was perform a surface recognition of the point cloud, and then perform a hole filling or a gap filling in case there was any gaps or holes inside the mesh. And for the case of a lowest level of detail, LOD 200, our simplest procedure was followed. Only the convex hull was applied in order to obtain the reconstructed mesh. Once these meshes were obtained, the next step was to convert them into an IFC model, to the generation of the IFC model. The procedure here still needs from some user input. This is a semi-automatic procedure because we don't know the full semantics of the elements in the cloud, in the mesh. So we need some input about the desired spatial structure and the mapping of the detected elements into IFC element classes and some additional semantics that we want to provide as users. The procedure is divided into 4 different modules, and in each of these modules, the user input can be made. After applying this, we obtained models in the schema, in the format of the schema IFC 4.2, that was the updated, the schema that was the latest release at the time of the publication of this paper. We have tested these models in different platforms, and all of them appear to open the model and to be able to work with it. These are the results obtained for the point cloud to mesh conversion. We have the LOD 500, in which we can see a very high level of detail. And then we have the LOD 200, in which we only have a rough representation of the elements of the bridge. And the same for the IFC model generation. Here we have a representation of the LOD 200, and here we have a representation of the LOD 500, sorry. And we get to the conclusion. The conclusion of this chapter is that point cloud data were used to create IFC instance models. I would like to add that using laser scanning data, we are able to get the as-is state of an asset and transmit this into digital models of the infrastructure, which is the objective of the digitalization of information nowadays. And with this, we reach the final chapter of this presentation, which are the conclusions. I wanted to organize these conclusions based on the objectives presented at the beginning. We have, having in mind the main objective, we divided it into 4 different ones, starting with the first of them, that was the development of general algorithms applicable to any 3-dimensional point cloud. And as I presented at the beginning, I developed different functions used by everyone working with point clouds so that the processing could be easy. The second objective was the creation of methodologies for the optimized analysis of registered point clouds of different structural systems. Well, this was achieved by the development of methodologies for both terrestrial and mobile laser scanning systems, and the classification of the structural elements in masonry constructions and in railway tunnel point clouds. The third objective was the development of inspection algorithms for describing the as-is state of an asset, and this was obtained or achieved by creating a study of pathologies affecting masonry arch bridges, more specifically piers, and the out-of-plane deformations in walls. And I can say that the methodology created for detecting the out-of-plane deformation of a masonry wall also worked fine with detecting pathologies for the spandrel walls of masonry arch bridges. Moreover, I've also created algorithms for the inspection of the railway power line. And the last objective of my thesis was the use of point clouds for generating digital models of infrastructures. And as I have just said, we used laser scanning data as a representation of the as-is state of an asset. In order to generate those digital models, we used open standards, and we have also added some semantic characterization to those digital models. And with this, I reached the end of my presentation, and now I would like to, I will expect some questions from the tribunal and everyone willing to ask. Thank you.
Well, Ana, can you hear me?
Yes.
So, well, Ana, thank you very much for your excellent presentation. Now it's time for the debate. This debate will start with Dr. Lucia Diaz as Secretary of the committee.
Hi, can you hear me?
Yeah, perfect.
Okay, thank you very much. Well, I would like to start my intervention by congratulating Ana for her presentation and, of course, for the work she did during the PhD. For me, it's a great pleasure to be part of the examination committee, and I must say that I really enjoyed the work. Well, the quality of the doctoral thesis is already proved by the fact that the thesis is a compendium of articles, and most of them have been published in scientific journals and international conferences. So, really, the thesis is already double-blind peer-reviewed. And moreover, 2 of the papers have been published in collaboration with international researchers, I think, well, from different research centers. And I think this is very important because it shows the relevance of the work from an international point of view. And well, with regard to the document, I would like to say that I really enjoy reading it because, well, the document is very well contextualized in the huge topic of transport infrastructure inspection. And in addition, all the chapters are very well linked. And, well, this is very important because when you work on a thesis as a compendium of articles, sometimes it's not that easy to give the document a final cohesion. But in this case, your document shows a very good progress in a way that the first chapter proposed methods for the automatic lead process of point clouds to extract useful information. And at the end, you are using that useful information for creating automatically IFC models. So in a way, the document has an introduction and a development, and also it is very well concluded. So congratulations for it, because it's not always that easy. Well, I have some questions, and the first question is about chapter 3. The main aim of the first 3 papers is to develop methods for automatically processing point clouds in order to detect geometric changes in ancient structures, such as, for example, masonry bridges and walls. You talk about change detection, but you don't have multi-temporal data. So finally, what are you doing is to detect deviations from an ideal geometry. For example, in case of the medieval wall, you make basically a distance to plane evaluation. So my first question is not a question itself, is, well, a question and also a suggestion, and it's related to scan versus beam. Instead of using a plane as an ideal geometry for comparison with the point cloud, why don't you use a beam model? I mean, in the last years, some articles were proposed for the evaluation of as-built buildings with regard to the ideal situation, and this comparison is given between scans and the beam model, which has not only geometry in 3D, but also semantics. So instead of comparing the point cloud to a plane, they are comparing the point cloud to a model itself. And as I said, this is what we know as scan versus beam, which is not scan to beam. So my first question is, have you considered to use beam models as the ideal geometry for detecting geometric change in infrastructures, or, I mean, these scan versus MIM methods are emerging in buildings, but why don't you use them in infrastructures? I mean, do you think it is interesting to use these methods in infrastructures? Do you think we can improve the results or have new results?
Yeah, sorry, 1 minute.
Yeah.
Well, first of all, thank you, Lucia, for your kind words, of course, as always. It's also a pleasure for me to have been working with you through these years of my thesis. And now, answering your question, of course, the ideal solution nowadays would be to use BIM models to perform this type of scan versus BIM procedures, right? Because the idea now is to use BIM models as a method, as a way to get digital twins of infrastructure. Of course, it has been working through these years with buildings, why not with infrastructure? And I know that the international effort is now all put on the creation of digital twins and BIM models in infrastructure. The ideal solution would be to have those BIM models created from planes and from the design. In the case of ancient infrastructure of aging infrastructure, it would be difficult to have the BIM model created from the beginning. But if we have the planes of those constructions, we can therefore build the BIM model and, of course, perform those measurements against the BIM model. That would be the ideal, and from my point of view, is the future and how the things should be made from now.
Yeah, I mean, sometimes when these methods are implemented, the BIM model is not really automatically created from the point cloud, but the BIM model is like the ground truth. It's manually created, and instead of having a plane to make comparison, for example, you have the BIM models that are manually created as ground truth. So it's, I mean, this is really used in building monitoring, but I haven't ever seen in infrastructure inspection. So it could be also, I mean, it's not, this question is not just a question, it's also a suggestion, because I think it could be also interesting for you to work on this line. Or, I mean, I'm wondering why these methods were not implemented already in infrastructure inspection. Yeah. But of course, the ideal situation would be to automatically create the BIM model from the point cloud. And okay, and this is also related with my last, well, it's not my last question, but the second question, which is related with chapter 5. In chapter 5, well, it's a very nice chapter because in a way you conclude your work. So from point clouds, we extract useful information, and then the useful information is used to create a digital representation of the infrastructure as an IFC. And you say that, well, each segment, because you previously segment the point cloud in order to get segments, and is, as in the point cloud you have holes, you are like filling the holes that are caused by occlusions. My question is related to this hole filling. I mean, how are you filling the holes in a way that, what are the limits of the hole filling? Are you using a mask? And this is one question. And the other question, or it's related to this, is, are you filling holes segment by segment? I mean, individually? Or are you filling holes considering the bridge as a whole? I mean, considering the other segments are the limits of hole filling.
Okay, well, first, answering your second question, I can say that my colleague in Munich created, performed those that feeling segment by segment, not considering the whole cloud. And answering your first question, I'm not pretty sure how he did it because I was not in charge of this part of the publication, but I can imagine that that I don't know how meshes work, but I can imagine that yes, he should apply some kind of a mask or a reconstruction that allows it to fill those gaps. Of course, this filling is not based on the real geometry of the elements of the bridge or of the pier or whatever element is being analyzed, but it is a way to obtain a final mesh in order to be able to convert it to the IFC model.
Okay, thank you. Yes, I am asking because I haven't seen a lot of details in the document, and I found this very interesting also because how much are you feeling? I mean, it's something, if you are doing it segment by segment, I can imagine that you need to have the limits defined by the shape of the segments itself or the elements, but sometimes it could be also interesting to consider the topology of all the elements conforming the bridge to direct this growing or this filling. But I found it very, very interesting. And well, just...
Sorry, Lucy. I would just like to add that we are working in expanding this paper into a full paper, into a journal paper, so we can, of course, take your advice as a consideration for the next publication.
Okay, thank you. So
thankful for your comment.
Okay, so well, just my last question is related to your future work. You mentioned different research lines. One of them is improving data classification with deep learning techniques, and the other one is exploring more in depth beam reconstruction or IFC reconstruction. So which of these two future lines would you most like to work with? And why IFC and not CTGML?
Okay. Well, answering your first question, I'm now really inspired by the creation of beam models and the use of IFC and other standards to create some of these beams. And I would really like to explore, since I am mechanics engineer and I studied construction as my first as my main degree, right? I would really like to combine these techniques in a way that to use the semantic data obtained from point clouds or from other methods, the damages that an infrastructure can be suffering, and being able to translate it into the BIM model to be able to connect those two parts of these research lines. And why IFC? Because in the two research centers that I've been working with, they teach me how to work with this type of data, although I've been exploring the CTGML, and I know also infra-GML, and I know that now they are kind of working together to create, I mean, OGC and Building Smart, they are working together to create an international standard. So finally, I think that these are not two separated lines, but they are going to reach the same point. So I'm not closing any doors, and and I will consider also working with infra-GML, of course.
Okay, thank you. So, well, that's all from my side, and congratulations, Ana, again.
Thank you.
I do not have more questions.
Thank you very much, Lucia. Well, an interesting debate. So it's time for Dr. Lindenberg. So, Dr. Lindenberg, you can connect and ask your questions.
Thank you very much, Mr. Chairman. Anna, I was really impressed by your presentation today. That gave a very clear overview of the topic. And what I really like is that you, on one hand, you give a clear introduction of generic algorithms that you use throughout your thesis work, like GANSAC and the Silency Analysis and the PCA analysis. And on the other hand, you show how to use them efficiently in inspecting different types of infrastructural assets. My first question, of course, I always have some questions. So my first question is, if you now look back at your work, you considered a lot of point clouds of these of the objects that you considered, and these point clouds, they had a certain quality or point density. So my question is, and I guess in most cases, either you acquire these point clouds yourself or they were given to you, but in a way maybe there was not always so much possibility for you to influence these point clouds, let's say, on acquisition. So now if looking back, I was wondering if you are satisfied with the point density that you had, where they was the quality of the point clouds and the point density, was it good enough for your projects? Was it maybe sometimes too much? So did you maybe had too much points? And if you want to let's say apply your methodology on a bigger scale, what would be your recommendations? Would you let's say improve the acquisition even, or would you on the other hand say, well, no, I had way too many points, and I have to consider ways how to reduce it?
Okay, thank you for your comments and answering your question. Well, I think that it depends a lot on the type of data, meaning if working with terrestrial laser scanning systems or mobile laser scanning systems. For the case of terrestrial point clouds, I'm kind of satisfied with the point clouds that I had, because I know that how difficult it is to perform a survey, and that all point clouds, to be able to align the point clouds, the scans acquired efficiently, that is pretty hard, because the misalignments can affect a lot in the results obtained, especially for the damage detection. And so in that case, I will not reduce the quality of the data, maybe the density, but not the resolution, let's say, the quality, right? Because I know how difficult it is to align different scans when performing a big survey. And for the case of mobile laser scanning point clouds, from my experience with tunnel point clouds, I can say that the data were really good. I'm very satisfied with the data obtained. Depending, of course, of the purpose, because if you want to detect, for example, some cracks in the concrete of the lining, it is pretty hard for the laser scanning. If these cracks are very fine, very small, it is very hard to detect them. But for my case, I'm very satisfied with the data, but I also know that the density is not needed. I was able to work with a colleague from the Technical University of Munich, that he was in charge of smartly reducing the point clouds in a way that important data are not lost. So, and we proved that the results are totally fine with lower density of the point clouds, but again, performing a reduction of points in an intelligent way, let's say. So I will say that not always a bigger data set is the best.
Okay, and how would you reduce point cloud? So what is the smart way? So how would you, maybe your colleague did it, but what would be your recommendation also for terrestrial laser scanning? You mentioned sometimes you had too much points.
Can you repeat it, because I lost the audio?
Sorry. So what is your recommendation? How should I reduce a point cloud in a clever way?
Okay, I definitely don't deeply know the algorithms applied, but it's based on how the points. For example, if you have a corner, let's say if you are scanning a building and you have a corner, in those spaces you will have more density of points, and not if you have a flat wall, because it's not needed there. So that's the kind of density reduction that I'm talking about.
Okay, that is clear. Then I was wondering, did you have any problems at intersections of segments?
Yeah, that is an issue when working with trimmed point clouds with sections, and then the ideal solution would be to have overlaps between sections to avoid those problems.
Okay, well, maybe when I go back, when I started to work with point cloud processing, then one thing that was frustrating at the time was a very good viewing software, and then Cloud Compare came, and that kind of solved that problem. So I was wondering if you now would make a software that could be something called like a cloud structure. So a software that people would give you some money to work on that for 5 years. So how would the cloud structure software look like that you could make to analyze, for example, a bridge or a railway tunnel? Because I think now you made many codes yourself and you programmed it yourself. But suppose you were asked to make something like Cloud Compare, but then specifically for analyzing structures, how would that look like?
Well, that's a very interesting question, and I think that it's very difficult to answer, but I can imagine that the first thing would be to make an inventory of the data, the classification of the data, and of course, it's not logical to think that heuristic methods can be applied. I think that when working with different kind of infrastructure, the idea would be to apply some machine learning, deep learning that already used neural networks to classify the points based on previous knowledge acquired with other data sets, of course, in order to train the neural network. And then, in order for the damage detection, that is really a hard task, because it's not the same working with a masonry arch bridge that working with a concrete bridge, that working with a steel bridge already software that performs this type of analysis, and maybe a software that uses ANSYS to be able to perform some law to represent the real state of the bridge, will also be applied.
But do you think that it's feasible to have such a software? Or do you think, well, no, the objects, they are so different, and so there are so many, let's say, different ways to process it, so that it doesn't make sense to make one software, and you should always use a kind of like an individual approach for each particular object?
Well, I have I don't know how to express it in English, but I would not put a final decision, because I think that it's not impossible, although there should be a lot of restrictions, of course. Not any type of structure could be entering that software, because that not make much sense.
And maybe a final question would be, so you mentioned already, and also in your discussion with Lucia, you mentioned that deep learning is it's of course very popular, but what problems do you expect that the deep learning will solve that now still exist in the topic of structural inspection? So what particular problems do you feel that are still existing that now that you would expect that deep learning could solve the coming years?
I mean, for inspection, I don't see it like deep learning could give so much. I think that deep learning, of course, it's always good to apply, not always, but I mean, I would prefer to apply, I see it more logical to apply deep learning to classify points, to label points, and not to perform the inspection of an asset. Because for that inspection, you need some restrictions, and those restrictions would be dependent on different norms, depending on the country. And so I will use this deep learning for the classification process. That is a really rough task. And the problem when working with point clouds and deep learning is that there are not so many data sets available for training those models. And for urban point clouds, you have every day more and more data sets, but for infrastructure, it's really difficult to have those open access platforms to be able to train your data.
So you say we should use we should generate more labeled bridge data, and then we can use that to better classify bridges using deep learning methods. Okay, thank you very much. I give back the floor to Jose.
Yeah. So thank you very much, Roderick. Well, finally is my time. Ana, first of all, I'd like to congratulate you on your excellent thesis, and I would also like to extend my congratulations to your supervisors. I found both your document and presentation very clear and to the point. And actually, I have an excellent opinion of your work and don't have any negative comment. The quality of the thesis has already been demonstrated through publications in high-impact journals, 3 publications, 2 conference papers, and a book chapter. However, I'd like to discuss with you some points and aspects of your research. First, I'd like to discuss with you the topics you have covered in your thesis and how they are connected. You work on masonry bridges, walls, tunnels, and power lines. So I understand that the work carried out for each case is not independent from the others. So my question is, how have you transferred the outcomes or knowledge from one case to the others? I mean, how are the cases connected?
Okay, thank you for your comments, Jose. And of course, I will answer your question now. Starting from the bridge point cloud classification, that really opened me the way, the path to be able to reach other results along the thesis. With the bridge classification, I learned how to manage point clouds. I learned different heuristic algorithms that everybody knows, but I didn't. I had no idea on dimensional analysis, principal component analysis, voxelization, all those basics that everybody has when working with point clouds. I learned through working with bridge point clouds. So that is my first step, and that is connected. That is connected through the whole thesis, because a lot of algorithms developed for bridge processing are used when processing a tunnel, and the assets are totally different. And then how I connect the bridges with the masonry wall. That is very easy, because I already said that I proved the results of measuring the out-of-plane deformations of the masonry wall in the spanner walls of the bridge, and it worked perfectly. And also the next step now would be to mix the results for for example, the piers detection, the damage detection in piers and the damage detection in the spandrel walls, and make a connection between them in order to get a more general concept on what is happening to that breach. So that is the connection with the masonry wall, and again, the algorithms used for the wall can also be applied further in the thesis, let's say. And then for tunnels, I already said that the algorithms come from the beginning, and the inspection of the power line, it is very simple, but I think that it is connected not only with my thesis in general, but also with my previous knowledge, which is construction and the study of the state, of the health monitor of the infrastructure. Although, of course, it's not the same talking about the structural health monitoring than inspection of the power line, but I think that that is not the damage detection in tunnels is not finished and can go a step further by detecting another types of damages. So that's how I see the connection. And of course, the final chapter, the digitalization of information, for me is connected with everything, because that should be the next step for everything that I did.
So very clear. Thank you very much. Well, Ana, well, let me ask you a second question. Well, you work on a timely topic. I mean, masonry breaches and tunnels. But well, in recent years, I've been working on steel truss breaches, well, built at the beginning of the 20th century, and I have realized that many of these breaches are in risk of failure. So, I would like to ask you if your methods and outcomes could be used for this specific structural type. I mean, steel truss breaches made of linear elements connected with rivets.
Okay.
So what's your opinion, Ana?
Okay, we are now working with, actually we're now working with a point cloud that has these big trusses, connections with steel bars, connected one with each other. And I hope that my algorithms, of course, they are not going directly, they cannot be directly applied to a different type of bridge if it is not a masonry arch bridge, but some modifications and the insight got from that processing can be used definitely for the analysis of other types of bridges. And I hope that this knowledge that I have can help us to process the bridge that I mentioned and to obtain good results and implement it further.
Thank you very much. Ana, well, a question about the error tolerance of your technique for masonry structures. You have identified some failure mechanisms, but it is not clear to me if you will be able to detect small cracks in masonry elements. Let's say cracks due to compressive or tensile loads with an opening around 2-5 millimeters. Can you say something about this?
Okay, this depends a lot on the resolution of the point cloud acquired. So it depends a lot on the survey made and the conditions of the survey, and of course on the size of the crack. Very small cracks are not going to be detected, and it is very simple. When you see the point cloud, if you cannot visually detect the crack, you cannot detect it automatically using some processing. Yeah, I understand what you mean. That's what I would like to say. That's how I see it.
I understand. Well, Ana, my last question. You have obtained very interesting results. My question is, how are you planning to transfer these results and outcomes to industry?
Okay.
Do you have any plan with your supervisors?
Okay. Nowadays, as I said at the beginning, very beginning of my presentation, we are working in several projects, and some of the outcomes of my thesis are already being used in those projects. So that's a direct connection, although it is not the industry per se, but it is some connection to the real world and working with other companies and from the private sector. So now, how I see my algorithms, they should be improved in quality in order to make them the language, make the language, the programming language. I mean, the programming language that I used needs to be converted into a different one in order to be able to transfer it into the industry. And moreover, I would say that nowadays that would not be enough. That's why I wanted to start working with BIM and IFC and digital twins. And I think that is the strong part, and that's how this knowledge and this information that is gathered thanks to the laser scanning systems, that is how this data can be standardized in a way that everybody understands. So using point cloud data and the semantic information extracted from it to generate data in a standardized format that everybody can understand. I don't know if this answers your question.
Yeah, it's perfect, yeah. So Ana, that's all. Thank you very much. Well, after this debate, it's time for any doctor in the meeting room to participate. Anyone wanting to participate can activate the microphone and camera. The supervisor, Dr. Riveiro.
Well, I don't know if you can hear me well.
Yes.
Okay. I just want to make some comments, basically to give thanks to the jury members for taking part in this dissertation, for your disposition, and mainly for your work or the paperwork that UVigo demands for a dissertation. Our pity is that we cannot host you in Vigo this time, unfortunately, and that way we are missing some important part like the warm defense being in person, but most importantly to celebrate together the Anna's dissertation. So I hope we have more opportunities in the future to celebrate these once or even twice if the pandemic is solved soon. I would like also to give or to take this opportunity to give public thanks to the supervisors of Anna during her stays at the University of Minho, also in TNO with Professor Michel Boms, who is today here, and also to Professor Bormann from Technical University of Munich, and also their teams. Because of the warm hosting for Anna, I'm aware that she was really happy in their stays, and I think that it was finally a very good experience, or they were very good experience for Anna's training. And finally, I would like to give thanks to Anna because of these last 4 years together working in the lab. Of course, because of the quality of the work done, which is being presented today, and I think that I cannot add so much more. But I would like to especially give thanks for your hard work towards the projects of the group, and also because of your attitude, and for making the lab or the team of the group remember that we are a group of persons and not only researchers. This is a very important issue that I wanted to emphasize here. And if the non-Spanish speakers allow me to do so, I would like to finish my words in Spanish. Porque me gustaría dar las gracias y felicitar al mismo tiempo a la familia de Ana por los valores que le han inculcado, por su humildad, por su perseverancia y sobre todo por sus valores hacia el trabajo en equipo, que son cosas que se en casa. Entonces, bueno, pues esto es que trabajar contigo estos años ha sido un placer. So from my side, there are no much more to say. So again, thank you all for taking part on this PhD and also in the dissertation. So thank you, Professor Adam. I can finish my intervention here.
Thank you very much, Belén Riveiro. So it's time for more questions, comments from any doctor from the audience. Would anyone like to participate in this debate? So, Ana, it seems that this is the end of the first part of the session. So the committee is going to leave the meeting room for the deliberation, and we'll be here again in a few minutes. So thank you very much.
Okay, thank you.